for students is that when they get several equations with several unknowns and they want to use elimination, they're misled. Remember the technique for elimination. You use every equation to eliminate one variable. Once you've done that, you then go on. So you say you had an n by n system. Once you have used each of those n equations to eliminate one variable, you then have a n minus 1 by n minus 1 system. And you keep doing the same technique where you eliminate one variable using all the equations. Unfortunately, students will be misled that they eliminate one variable using some equations, but then they see that they could eliminate a different variable using the equations. They will then unfortunately, that will lead to go into this loop where you sort of you keep trying to eliminate variables using equations, and you eventually come back to the same equations and the same variables. And so you get this like loop that you've gone through. You get lost. And so rather than getting lost, we will tell you the strict sort of technique to use so that you don't get lost. So this is a technique where rather than giving you all the freedom, we will say you do it this way, and this is how you do it. In general, it's not the best way to do it because you're not using the actual structure of your equations. But the good thing is that you don't get that this technique will lead you to either finding that you have one solution, no solution, or infinite number of solutions. It will not allow you to sort of just sort of get lost and waste a whole bunch of your time and not get anywhere. Okay, so section 6.2, Gaussian elimination and the matrix methods. So this will include both a little bit of the Gaussian method and a small bit of the matrix methods. So first off, let's recall matrices. Let n sub n be just the set 1, 2, 3, ... up to n. Let m sub n, m by n, be the set of all functions from the Cartesian product of n sub m cross n to, say, some field. This is the set of m by n matrices. And so a matrix is just this set of functions. In general, we will use an array to represent a matrix. So we can just think of a matrix as some array of numbers. We can rewrite a system of linear equations as a coefficient matrix times the variable matrix, equaling to the non-homogeneous matrix. So in general, we can write a system of equations as some matrix, coefficient matrix A, times some variable matrix X, equaling some non-homogeneous matrix B. The techniques, well, if you wanted to solve 2x equals 6, you would just divide both sides of the equation by 2 to get that x is equal to 3. That's how you solve a system of linear equations, if you can actually do it. If you can find an inverse you just multiply the inverse matrix by both sides of your equation. And so you get that your variable matrix, your solution, genius matrix, if this inverse exists. So let me give you the idea of Gaussian elimination, solving this system of equations. 2x plus y equals 7. X minus 2y equals 1. Okay, so first, let me do this regular elimination. And then let me show it. Well, let's say that this is Gaussian elimination. Okay, I'm going to show you really Gaussian elimination. Using sort of our old technique, our old notation. And how it corresponds notation. So this will not actually be a matrix technique, but it will be a matrix notation. Okay, so first off, I have here a 1x. So let me rewrite that as x minus 2y equaling 1 and 2x plus y equaling 7. So let me put the equation where it has the 1 in front of x. Let me bring that and put that at the top. Next, let me try to eliminate the x. So now I'm going to try to eliminate x. Okay. And so let me multiply the first equation by -2. And maybe I'll call this R1 and R2. So I'll multiply the first equation by -2. So -2x plus 4y equaling -2. And let's add it to the second equation. 2x plus y is equal to 7. So let's add these together. And so I get, well, the 2x's cancel. I get 4x plus 4y plus 1y is 5y. And 7 minus 2 is 5. Now, I'm going to use this first equation to solve for y. So let me rewrite that equation. R minus 2y equals 1. Okay, so add another page here. So now I want to solve for y. So let me divide both sides of my equation by 5. So I get y equals 1. Well, I still want to use the first equation, so let me just write it down so I keep track of it. So now, let me determine what, let me actually eliminate y here by using these two equations. And so let's call this S1 and S2. And so let's eliminate y. So I have x minus 2y is equal to 1. Let's multiply the second equation by 2. I have 2y equals 2. And now let's add these. So if I do that, I get x is equal to 3. And I got that y was equal to 1. So now, let me do this in a matrix notation. So let's sort of rewrite this, but sort of in a matrixy sort of way. So first, I'm going to be lazy. Rather than writing the x's and y's, I will only write the coefficients. So 1x, 2x minus 2y equals 1. So 1x minus 2y equals 1. 2x plus 1y equals 7. Okay, so now I'm going to pivot. So the technique that I'm going to use is what's called pivoting. This element here is called the pivot element. Okay. It was eliminate x. So it's the pivot is the eliminate object. Okay, so now to eliminate this x, what I'm going to do is I'm going to multiply the, and maybe I'll write it here. I will do the following. I will multiply the first row. I'll take the second row. I'll subtract from it 2 times the first row to give me a new second row. And so I have here the second row. I'm subtracting. So if I do that, I get, well, the first row is the same. I haven't done anything to it. I multiply the first row by -2 and add the second. -2 times 1 is -2, plus 2 is 0. -2 times -2 is 4. -2 times 1 is -2 plus 7 is 5. I get the same system here. Now, let me take this and divide by 5 to solve for y. And so let's take R2 and divide by 5 to give me a new R2. And so I have 1, -2, 1, divided by 5. 0 divided by 5 is 0. 5 divided by 5 is 1. 5 divided by 5 is 1. So we have the same systems that we had from before. Now, let's multiply the second equation to the first equation to get a new first equation. And so I have 0 plus 1 is 1. Negative 2 is 0. 2 plus 1 is 3. I have 0, 0, 1, 1. Now, if I rewrite this as a system, as a line, system linear, to get 1x plus 0 is 3. No x plus 1y is equal to 1. So I have the same thing. Now, in general, we don't, when we're doing it in this matrix notation, I don't do this. We can combine several of these into one, so it won't look nearly as long. Of course, when you're doing it elimination by hand, you can't really shorten it by much. Okay, so now let's do on page 574 Gaussian elimination to solve each equation. So the idea with Gaussian elimination can be summarized as follows. Solve for x first, using the first equation to eliminate all the x's. And now, if you don't have an x in the first equation, find an equation that does have an x in it, interchange those so it becomes the first equation. Use x to use the first equation to eliminate x in all the other equations. Then eliminate y, eliminate z, etc. So Gaussian elimination is eliminate x first, then y, then z, etc. And that's it in a nutshell. Okay, so let's solve the system. So first, let me rewrite this as a matrix. 1x plus 2y minus 1z is equal to 2. 1x minus 3y plus 2z equals 1. 1x plus 1y minus 3z equals negative 6. So let's pivot. And so let's take the second equation, subtract the first equation to get a new second equation. Let's do that first. So 1, 2 minus 1. Let's multiply this first equation here by negative 1, add to the second. So I'll just do 1 minus 1, 0. Negative 3 minus 2, negative 5. 2 minus the negative 1, 2 plus 1 is 3. Um, 1 minus 2 is negative 1. Let's make this 0. And so I'll take the third row, subtract from it the first row to give me a new third row. 1 minus 2, negative 1. Negative 3 plus 1, negative 2. Negative 6 minus 2, negative 8. Okay, good. And so let's try to, actually it's probably better, it'll be algebraically a little bit easier if I interchange the second and third rows. So let me do that. So I have 1, 2, -1, 2, 0, -1, -2, -8, 0, -5, 3, -1. So let's pivot. Okay. I'm going to do fraction-free pivoting. So let's try to eliminate the 5. So let's take third row, subtract 5 times the second row, bring a new third row. Well, so I have 1, 2, -1, 2, 0, -1, negative. Let's multiply by -5. 0 plus 0, 0. 5 minus 5, 0. 10 plus 3, 13. Really? 8, 40 minus 1, 39. So now that I've done that, let me use the following technique, backward substitution. So this is backward substitution. So if I have that after I've used these elementary row operations, these changing, adding, multiplying, interchanging rows, and I get something that looks upper triangular, meaning that the lower triangle here is all zeros. So this is upper triangular. Then I can use what's called backward substitution. So let's look at the very last equation. 0x plus 0y plus 13z equals 39. So I get z is equal to 3. Now, let's look at the second equation. So now, let me add another page. Now I have 0x minus y minus 2z is equal to -8. And so I get that negative y minus 6 equals -8. Add 6 to both sides of your equation. So y, negative y, is equal to -2. Divide both sides of your equation by -1, so y is equal to 2. Lastly, let's try to solve the first equation. So 1x plus 2y minus z is equal to 2. So I have here that x plus 4 minus 3 is equal to 2. X plus 1 is equal to 2. Subtract 1 from both sides. So x is equal to 1. And that is my solution. Write each system as a matrix. Solve it by Gaussian elimination. If a system has infinitely many solutions, show a general solution. Okay, so let's do this. So I have 1, 1, negative 1, 1, 1, 1, 3, 3, negative 1, 5, 2, 12. Okay, so now let's pivot and let us eliminate everything below the pivot. So I'll take the second, doesn't really matter, second row, subtract from it the first row to get a new second row. I'll take the third row, subtract from it 3 times the first row to get a new third row. And so I have 1, 1, negative 1, 5. So let's subtract. So 1 minus 1 is 0. 1 minus 1 is 0. 1 plus 1 is 2. 2 minus 5 is negative 3. 3 minus 3 is 0. 3 minus 3 is 0. 3. No, that's 3 minus 1 is 2. 12 minus 15 is negative 3. So I'm done, basically. So now, well, actually, let me just show you the last step. So let's take, let's pivot. So I can't pivot here. There's nothing below it that's non-zero. So I've got to go to the 2. So let's pivot. So let's take the third row, subtract from the second row. And so I have 1, 1, negative 1, 5, 0, 0, 2, negative 3, 0 minus 0, 0, 0 minus 0, 0, 2 minus 2, 0, 3 minus 3, 0. So now what you notice is that I have a row of all zeros. Okay. If I have a row with all zeros, then this will imply that this is a dependent system. And it will be a, well, let's say P parameter family of solutions, where P is the number of rows that are 0. Since there's only one row that has all zeros, then this implies that this will be a one parameter, this will have a one parameter family of solutions. Since it has one row of zeros. Okay. So now let's do this. So I have 0x plus 0y plus 0z equals 0. So there's nothing I can do there. I have 0x plus 0y plus 2z equals negative 3. And so I have that z is equal to negative 3/2. Okay, so now let's plug that into the first one. And so I have 1x plus 1y minus z 3/2 is equal to 5. And so let's add, well, doesn't really matter. Let's solve for y. So I have y is equal to negative, okay, 1 second. Let's see if I can, okay, let's see if this works. Okay, move, please, move, move, move. Okay, so it's moving now. So let's subtract x from both sides. 5 minus 3/2 is, well, 10/2 minus 3/2 is 7/2. Okay, so let's write our solution. So let's, I don't know, let's x equal alpha or something. A parameter, doesn't really matter what I call it. So now I have that alpha, negative alpha, minus 7/2 and negative 3/2 is a 1 parameter family of solutions. And that is the solution to my system. And that is my solution. In this case, it looks like a line in 3 space. Oops. Elementary row operations. So a interchange of row I with row J is called a type 1 row operation. This denotes the fact that we interchange rows I and J. KRI interchange, well, gives us a new ith row. So this is a type 2 row operation. This says that I should multiply the ith row by the constant k to get a new ith row. A type 3 row operation denoted by r sub I plus k r sub j, giving me a new r sub I. So this says to add the ith row to a multiple, a k multiple of the jth row to get a new ith row. Similarly, you get the same thing for column operations. So instead of calling these rows, you can do the same thing for form. There. Row echelon form. A matrix is in row echelon form if, first, the first non-zero entry in each row is 1. Second, these lead entries appear further to the right as we move down the rows of the matrix. 3, any rows containing only zeros are at the bottom of them. So this is similar, it's 13, to what we had. Oh, I didn't write the zeros there. Let's see. Well, this is if I divide this guy here by 2, then this would be an element. This would be in row echelon form if I had written it this way: 1, 1, minus 1, 5. If I had divided by 2, this would be in row echelon form. Okay. Reduced row echelon form. This is what I actually usually do it in fraction-free form, but reduced row echelon, come on. Reduced row echelon form. Okay, it's back. A matrix is in reduced row echelon form if row echelon form and the entries above the lead entries are 0. And so if I have it where not only, I made it lower triangular, but I also eliminated where I had the 1s, I eliminated things in the same column above those pivot elements. Page 576, problem number 69. Each system contains a different number of equations than variables. Solve each system using Gauss-Jordan elimination. If a system has infinitely many solutions, show a general solution. Okay, so in this case, we only have 2 equations, but 3 unknowns. So really what it looks like is the following. Looks like 1x, 2y, 1z equaling 4, 3x minus 1y minus 1z equals 2, and 0 equals 0. So what you'll notice is that must mean that I have an infinite number of solutions. So if I would have written it as a 3 by 3 system, I can see that I need, well, unless this is inconsistent, that it probably has an infinite number of solutions. I'll be able to figure that out once and so let me pivot. So let's take the second row, subtract 3 times the first row to give me a new second row. Well, the first row will be the same. Multiply the first row by negative 3 and add to the second. So 3 minus 3, 0. Negative 1 minus 6, negative 1 minus 3 times 2, negative 1 minus 6 is negative 7. Negative 1 minus 3 times 1, negative 1 minus 3, negative 4. 2 minus 3 times 4, 2 minus 12, negative 10. 0, 0, 0, 0. So I'm done. Now let's try to find the solution. So obviously 0 equals 0 is the last row. Let's look at the second equation. 0x minus 7y minus 4z equals negative 10. Let y equal, let's say, 4t. Then I have negative 7 4t minus 4z equals 10, negative 10. Wait. Let's let y equal 2t. And so I get negative 14t minus 4z equals negative 10. Add 14t to both sides of my equation. Oh, I see. No matter what, I'll get a fraction. There's no way I cannot get a fraction by way of that. Okay. I'll just have to live with it. Okay, let y equal 4t. So I have a negative 28t minus 4z equals negative 10. Add 28t to both sides of your equation. Divide by negative 4. And so z equals 5 halves minus 7t. Let's look in the first equation. So the first equation, I have x plus 2y plus z is equal to 4. So I have x, that's plus 8t plus 5 halves minus 7t equals 4. And so I have x plus t plus 5 halves equals 4. So x is equal to, subtract 5 halves from both sides. So 10 halves minus 5 halves. 8 halves minus 5 halves is 3 halves. Subtract t from both sides. So I have a one parameter family of solutions of the form 3 halves minus t, 4t, 5 halves minus 7t. And this is for all real numbers t. So that gives me a one parameter family of solutions for my system of equations. And that is my answer.